Hello, everyone. I'm Charlie Sharpless, the Assistant Director for Research at Princeton University's Andlinger Center for Energy and the Environment. Today, I'm again pleased to introduce our Distinguished Postdoctoral Fellows webinar series. The Distinguished Postdoctoral Fellows program at the Andlinger Center supports outstanding young researchers working to solve pressing problems in the environment related to energy use and environmental protection. Fellows collaborate with multiple investigators at Princeton to advance the center's mission of finding practical solutions for sustainable energy. Consequently, their research integrates multiple disciplines, from fundamental science to engineering, architecture, social sciences, public policy, and beyond. The result is a breadth of work that we're very excited to highlight with this summer webinar series. The fellows have accomplished amazing things, published regularly in high-quality journals, and gone on to faculty positions at leading universities. Before continuing, I'd like to note that if you have a question at any point during the talk, please type it into the Q&A box. At the end, we will address as many questions as we can fit into the available Q&A time. Today, our speaker is Dr. Luis Ceferino. Luis holds a BS in Civil Engineering from the National University of Engineering in Peru and an MS and PhD in Structural Engineering and Geomechanics from Stanford. Over the past year, he has worked with Dr. Ning Lin, an Associate Professor of Civil and Environmental Engineering. Research in Dr. Lin's lab is broadly aimed at developing approaches for risk assessment and prediction in hurricane events in the context of changing climate, and how society can work to manage this risk. Please join me in welcoming Dr. Lin, who will introduce today's talk.
Hello, everyone. Thanks for joining us on this seminar. Thanks, Charlie, for the introduction. My name is Ning Lin. I'm Associate Professor in the Department of Civil Environmental Engineering at Princeton University. My research has been focusing on hurricane hazards risk, particularly to model the hurricanes and their hazards, including extreme wind, storm surge, and rainfall flooding, and particularly what's their impact on the coastal infrastructure systems. And we're particularly interested in to study how climate change will affect these hazards and risk, and how do we develop effective engineering and policy strategies to mitigate the risk and adapt to climate change. So Luis joined us last year, and he has been working on hurricane resilience for infrastructure systems, particularly the power system or distributed power systems. Before that, Luis received his PhD from Stanford University in Civil Environmental Engineering, worked on the earthquake engineering, particularly the impact of large earthquakes on urban systems, including power systems. So today he's going to talk about disaster resilience of distributed energy resources for both earthquakes and hurricanes. And Luis is going to leave us next year to join the faculty at NYU to continue to study disaster resilience for multiple hazards. So without further ado, I would let Luis to take over.
Hi, everyone. First, thank you, Ning, for such a warm introduction. Also, thank you, Rob, Sarah, Adrienne, and Charlie for organizing and inviting me to this seminar series. It's very exciting to see such a large and broad audience. I wish I could see you in person, but I'm happy you can still join me virtually, and I'll show you my research on the disaster resilience of modern power systems to both hurricanes and earthquakes. So I'll start by showing you this picture here. This picture shows the nighttime satellite imagery of Puerto Rico pre and post Hurricane Maria. And I like this picture because it's self-explanatory. Our power systems are extremely vulnerable to natural disasters. In fact, in Puerto Rico, Hurricane Maria in 2017 left multiple cities without power for very long times, in several cities for up to 9 months, which is huge. And this is not an isolated event. Hurricane Sandy also in 2012 left most of New York City and the northeast part of New Jersey, where we have close to 10 or 8 million customers without power for several days. And it's not only hurricanes, also earthquakes. For example, in 2014, the Napa earthquake in California left 70,000 people without power for several days. And this was only a medium-sized earthquake of magnitude 6. So our systems, power systems, are very vulnerable to natural disasters, as I mentioned previously. And this happens because of a combination of factors. First, our traditional power systems are heavily centralized, which means that our power generation occurs in very few spots and in very large quantities in power plants, instead of happening in multiple cities in fewer quantities. And then our power systems or our energy has to travel through very long distribution and transmission lines to reach the end users in our cities. And usually these distribution and transmission lines are old and vulnerable. As you can see here in the picture to your right of the power of the distribution lines in Puerto Rico after Hurricane Maria in 2017. This, together with the low redundancy of the system, makes our power grids very, very vulnerable to natural disasters. However, the introduction of new technologies to a power grid might change that reality. We're introducing distributed energy resources to the grid in the form of solar panels or behind the meter batteries that are going to change the system, because they are decentralizing the system, meaning that multiple users now are generating their own energy on the roofs, literally. That means that the energy will avoid the long and vulnerable transmission and distribution lines if we increase the adoption of these distributed energy resources. There is a rapid growth in the market. Photovoltaics or solar panels are growing at a 7.5% rate in the US, which is very high. And predictions say that 20% of the global generation might come from PVs by 2050. And this prediction might be a bit updated because more recent studies mention a higher share of solar energy by 2050. So this, together with the deployment of microgrids, which are a cluster of loads, people or households or stores consuming energy, and also a cluster of loads and distributed energy resources, might provide an opportunity to increase the resiliency of the grid. Microgrids can work on island mode, meaning that when there is an outage, they can disconnect from the grid and produce and sustain their own generation and distribution, have shown successful results after disasters. For example, the Roppongi and Sendai microgrid worked pretty well in 2011 after the Tohoku earthquake. And just for reference, this was a massive earthquake of magnitude 9 that caused the failure of the huge Fukushima power plant in 2011. In the US, there are also successful examples of the resiliency of microgrids when the HEB store had their microgrid working well after Hurricane Harvey in 2011 in Houston. And it actually worked so well that emergency responders used that as a base for several days during the hurricane. And while in research, we have a better understanding of what's the economic and environmental benefit of distributed energy resources, we know far less about their benefit in terms of resiliency to natural disasters. So this is going to be the focus of my talk today. And I'm going to show you a project on distributed energy resources and their resiliency against earthquake hazard. And then I'm going to show you another project on hurricane hazard. And I'm going to finalize with my conclusions. So let's start with the earthquake hazard. So here, our focus is on understanding what are the resilience gains of adopting these distributed energy resources in a city. Particularly, our objectives here are to create a quantitative model that is able to capture earthquake analytics and couple that with the generation for distributed energy resources. And we're going to focus on rooftop solar panels, as in the picture that I'm showing you to your right here. And we're going to see what's the benefit of having microgrids and sharing energy, meaning that the houses here that you see here would be working in such a way that they could share energy. And we're going to see an application to San Carlos City in California for earthquake hazard. And this project was conducted with the advice of Professor Anke Nimijan and Professor Ran Rajagopal, and also in collaboration with Dr. Sid Patel and the PhD students Chenin Liu and Tao Sun at Stanford University. So here we first define our metric to assess the resiliency of these microgrids. And our metric was a risk metric based on the likelihood of failure of microgrids. That means that they will not be able to deliver enough power to sustain the demands during an earthquake aftermath. To explain that further, let's assume that in the circle in red here, we have certain houses here. I'm showing you that there are footprints in these gray polygons here that are going to have or are going to adopt a microgrid here, and they're going to have solar generation in these yellow dots here. And what we're going to assess here is what's the probability of the demand exceeding the supply. So that's our risk metric. I'm not going to show you the formulation, the mathematical formulation behind it. For that, you can find it in a couple of publications we have here, but I'm just going to walk through you through our framework more conceptually here. And the framework of how we analyze this is subdivided in 3 steps here. First, and this framework, I should say, it's inspired or it's designed as we do in the performance-based earthquake engineering framework here, where first we analyze the ground shaking, the effect of the earthquake on a large geographical extent, and then we assess what's the damage to the infrastructure as a result of the ground shaking, and we finalize by assessing a decision variable or a metric that we're interested in. In this case, we're going to assess both the demand and the supply of the power generated by these solar panels. Here, so I'm going to walk through through these 3 modules here that we have in the analysis. First, the ground shaking, and here we assess a very large earthquake scenario here, mimicking the magnitude 8 earthquake that happened in San Francisco almost 100 years ago. And it's a massive rupture that passes through the San Andreas fault here. You can see the geometry here and the line is in red here. And you're seeing our case study in black here. This is San Carlos City, where close to 8,000 houses are. And in green, I'm showing you the levels of shaking intensity through the whole Bay Area here. So then we assess ground shaking here through the average spectral acceleration, which was developed by Professor Dávalos from the Universidad Panamericana in Mexico, and also Professor Miranda from Stanford University, which in this metric was demonstrated by these 2 researchers that works very well for the low-rise wooden houses that we find in San Carlos City in California. So this is module 1, and then in module 2, and this is, I guess I should mention also that this is what the picture I showed you before, the distribution of houses, that corresponds to San Carlos City, and the yellow dots also correspond to where the solar panels are. So then we go to the module 2, where we evaluate what's the damage state of the buildings there. So here we assess red tagging for 1- and 2-story wooden houses, which is what we find in California. And they tend to be vulnerable to earthquakes. As you can see by this picture here, that of a wooden house that collapsed, it had a soft story mechanism and collapsed after an earthquake. So Professor Eres, I should say now, from Universidad de Santa Maria in Chile, and Professor Miranda from Stanford University developed analytic formulations to assess what's the likelihood of a red tag of the building being so damaged you could not get into the building, given the ground shaking that we saw in the previous slide. And something that might seem intuitive, but it's changing the power infrastructure, is that now the building infrastructure is going to be coupled with the power infrastructure because the solar panels are on top of our buildings. That means that if the building fails, then also you might decrease your likelihood of harvesting energy, which is something that, as I said, is intuitive, but it's going to fundamentally change the behavior, or it's going to fundamentally couple these 2 types of infrastructure, building and the power system. And this is something we're taking into account in our analysis. We evaluated tax assessor data to get the footprints of the houses and also their areas and their structural characteristics needed to conduct a risk analysis in San Carlos City. Again, there are 8,000 residential buildings here. And out of our analysis, we saw that 1% of the buildings might be red tag, the ones which are 1-story in San Carlos due to this earthquake scenario. And the 2-story building has a higher probability of collapse because they are heavier and tend to have less wall density in their building plant use. So this is the second module, and then on the third module, it's subdivided into 2 parts. The first part of the metric is assessing the supply, the generation during the earthquake aftermath, and for that we evaluated the weather station in Bakersfield, California, where we focus on global horizontal irradiance here, which gives you, which generates energy in combination with the solar panel here. And just for you to, just for clarity, this global horizontal irradiance is time varying. And we model that with a beta distribution using the work by Laird and also Dr. Patel at Stanford University here. And you can see here that irradiance varies. As a result of the time during the day, you have more irradiance during daytime than during night or very early in the morning. And you also have more irradiance during the summer than during the winter, for example. Those are very important factors for the resiliency later that we'll see later on. So we combine these analytic models with predictions of photovoltaic adoption. The PhD student Yu and Professor Raja Gopal at Stanford University train computer vision model on solar panels and satellite imagery. So we're able to use the predictions of where the solar panels are and what sizes they have in the whole United States. But we were focusing on San Carlos City. So that's the yellow dots that you see here are actually where our predictions say the solar panels are. So we were able to leverage that in our analysis. And we saw that only 8.5% of the houses have solar panels. And this is information up to 2017, if I'm recalling correctly. It should be 2017. So then we analyze, or we couple this analysis with analysis before on the vulnerability of the buildings. And as I was mentioning, the damage state of the buildings are not coupled with the functionality of the solar panels. We assume here that if the building is damaged enough to have a red tag, we won't be able to get the energy out of the building. And this is one side of the analysis. Then we focus on the other side of the analysis, which is the demand. And for that one, first we study what were the pre-disaster power loads in San Carlos City. We base our analysis on smart meter data. We got a large portion of the data in that city, 22%. And then to actually analyze the entire portfolio there, we use a stratified sampling according to the building area, because we saw a strong correlation of how big the houses are with how much energy they consume. And then for assessing post-earthquake conditions, what we did was to use a very simplified formulation where we assume that based on empirical data, we assume that people might reduce their consumption to 50% or 30% of their previous demand, just to sustain very basic energy needs related to refrigeration or air conditioning. So we use these two factors here. Then that was demand and the supply. And then we analyzed finally how people can share energy through microgrids or clusters. So here we got inspiration from the design of Brooklyn microgrids. The Brooklyn microgrids are already sharing energy between people who are in close proximity. So if you have a PV, a solar panel, and you generate more than what you need, you can sell your energy back to your neighborhood. So we got inspiration from this and assessed that in the future, people in San Carlos might adopt microgrids with households that are in close proximity to one another. And for that, we use a k-means algorithm to cluster where potential microgrids could be, using a variation of the classical k-mean algorithm to have the same group size in each microgrid. And we tested multiple microgrid sizes, but here I'm showing you a cluster of 20 households per potential microgrid here. And this is the last piece of the analysis. So then we run our whole risk analysis. And here, what I'm going to show you in the plot I'm showing you the plot in the left here of the slide is the cluster risk. This is the risk metric I talked to you about a few slides ago, where we're measuring what is the likelihood that each microgrid will not be able to sustain their demands. So each dot here is representing the risk of each microgrid here. And on the x-axis here, I'm showing you different seasons of the year. And you see that the risk varies according to the seasons, because generation is higher in some seasons like the summer and lower during the winter. So here, we're supposed to see box plots, but we don't see them. We see just a line here because most of the microgrids have risk of 1, meaning that they are very likely to not be able to sustain their demands. And that makes sense because the adoption is still very low. It's just 8.5%. Other things we can see from this plot is that during the summer effective, we have lower risk because we have higher generation. This is something we can, it's intuitive because of how much more generation we have during the summer than during the fall. So we didn't stop here. We say, okay, now we have enough power to sustain the demands, given there is a complete outage of the traditional power grid. But let's see what happens if people start adopting more. So we, under a net zero adoption, meaning that each house might install solar panel sizes that will produce an average as much as they demand during the whole year, we assume 2 adoption rules. First, we studied an overall adoption rule where we say, okay, let's the market do its work, and so that the people who adopt the first are the people who save the most. And these tend to be the largest consumers in the city. So here we end up with very non-uniform distributions of who adopts. And so microgrids would have all the houses with solar panel, whereas other microgrids would have 0 houses with solar panel. Then we tested a more even adoption rule, where we let the largest adopters to adopt first, but from each microgrid. So in each microgrid, the largest adopters would adopt, but we would end up with the same number of houses with solar panel in all microgrids, which is more a more uniformly distributed adoption than the overall adoption rule. And we tested these 2 policies here in the next slide. I'm showing you the overall adoption on the upper plot, and then the even adoption in the plot below. And the first thing you can see here is, first you see the boxes now, meaning that the risk has lowered from what it was, close to 1 before. And you can see that for a 20% adoption rate, the risk decreases to close to 50%. So on average, the median microgrid all makes it on average. And this is a significant increase from what we saw before, where all the risk was close to or lumped close to 1. Then the other thing that is important to notice from these plots is the size of the boxes here, meaning that if you are under the overall adoption, that means that if you let just the market do its work, you end up with microgrids which do very, very well, but also with microgrids which are going to do very poorly, because they don't have any people in the house in the microgrid that has adopted energy. Whereas in the even adoption, we end up with a more fair distribution or more uniform distribution of risk. And this is something that we're seeing here for an analysis over the entire year, over all seasons of the year. But you can see the same kind of trends also during the summer. Here is the same plot, but for the summer. And under 20% adoption rate, first you can see that the risk decreases by significantly here to close to 5% or 7% under the overall or even rule. This is the median value here. But you still, even though the risk is better, you still see these disparities these disparities here in the behavior of different microgrids, triggered by this uneven distribution of the people who adopt in the case of the overall adoption rule, where the market just do its work. So this concludes the first part of my presentation. And just to summarize that, we saw how we can create models to quantify what's the resilience gain of distributed energy resources and microgrids, and seeing how different ways of adoption can introduce disparities or not to our communities. And that was an analysis on a city scale, San Carlos city scale. Now we're going to see a different analysis for hurricane hazard here. And the focus is going to be on a macro scale. Here, we're going to focus on the macro scale again, and we're just going to see the supply side. What's the solar generation capacity during hurricanes? Specifically, our focus here is going to be on developing a model that it's able to couple a few things. First, hurricane analytics, and then it's going to merge that with how solar panels can generate energy during hurricane cloud conditions. And it's going to further couple that with solar panel vulnerability as a result of high wind conditions. And we're going to see the application of that to the entire east coast of the United States. And this project was developed also under the guide of Professor Ning Ling and the collaboration of the PhD that she from Princeton University. So here, this is our framework. Again, here our resilience metric is the accumulated solar generation during hurricanes. And as you can imagine, solar generation here is very coupled with seasons, and hurricanes are also coupled with seasons. So we're going to see a strong coupling effect there that you don't see during earthquakes, because earthquakes are uniformly distributed over time during the whole year. So here, just to walk you through our analysis, we're going to assess this metric under 4 modules here. First, we're going to assess hurricane intensity, where Professor Ning Ling has plenty of expertise in generating hurricane data, their categories, their wind speeds, and their hurricane tracks, for example. And we're going to couple that with a part that was newly developed during my postdoctoral appointment here, which tracks how the solar generation decay is associated to the cloud conditions that the hurricane brings. We're going to further couple that with a model for solar panel functionality that measures what's the likelihood of the solar panels failing associated to very high wind conditions that the hurricane brings. And we're going to merge everything to assess what's the solar generation during a hurricane emergency response. So let me walk you through these modules here in the analysis. So here, we assess for the hurricane analysis, we use hurricane data developed by Professor Marsoli and also Professor Lin here at Princeton University, based on a global circulation model that captures or characterizes atmospheric and oceanographical conditions that can capture current climate, but also future climate. That coupled with a full physics-based tropical cyclone modeling that, as a result, can generate hurricane portfolio, hurricane catalog that contains their genesis, their tracks, their wind profiles, and other important features. And here I'm showing you 2 plots. One, the plot at the left or the center of the slide, you can see the track of the hurricane and some of its geometric features, like the radius of maximum wind in red, and also the radius of the outermost closed isobart in green here. And to the plot in the plot to your right here, you can see the full suite of hurricanes in the catalog. Actually, we assessed close to 5,000 hurricanes, all the way from tropical storms to Category 5 hurricanes. Here, so this is the first piece of the analysis. And then for the second piece of the analysis, how irradiance decay during hurricanes, I want to show you what's the global horizontal irradiance map at 3 p.m. on August 29th of 2006. And this is not at random. Here, the global horizontal irradiance is higher where the yellow shades are. And then I want to show you a comparison of that 1 year before. This is global horizontal irradiance the same day at the same time, but Sandy was happening here. And you can see from this plot that the hurricane conditions decrease or make the irradiance decay when the hurricane is on top of those locations here. And while this is just one snapshot of what's happening, you can see this consistently over different times of this hurricane and also over other hurricanes. So using that, using that idea, we assessed and coupled 2 databases, 2 very large databases. First, best track data with past hurricanes that occurred and we focus on the Atlantic basin here. And then we coupled that information with NRL solar irradiance data that shows or that has irradiance for the last 20 years at a 4-kilometer spatial resolution and at a 30-minute also temporal resolution. And the coupling of these 2 data sets, it's still a massive data set of close to 100 gigabytes here. So this is the suite of hurricanes we analyzed here. There are 20, it should be 22, but here I'm showing you 21. Yeah, 1 is missing anyway. So then I'm showing you here how how a metric for irradiance decay varies associated to with the distance from the site to the eye of the hurricane. So here, delta here is showing you a logarithmic deviation of the irradiance measure from the irradiance median here. And as you can see here, this metric starts from -2 and moves all the way to 0, where you have no effect of hurricanes on the irradiance for distances close to 600 kilometers here. And the different colors are just showing you different hurricanes here. So out of our analysis, we tested multiple features, and we saw that distance to the eye of the hurricane is a very good predictor of the irradiance decay. And we also tested the hurricane category here. And this is what I'm showing to you here in the plot below, where you can see this metric for irradiance decay with the hurricane category here. And you can see that trend here that as you have a higher category, you have a more intense decay on your ability to harvest energy from irradiance. So these two are very good predictors of irradiance decay, distance to the eye and hurricane category. So this was the second piece of our analysis. And using that data set here, we develop a statistical model based on mixed effect regressions that tracks how irradiance decay associated to different hurricane characteristics here. And here I'm just showing you the functional form without going into further details. The functional form has a logarithmic growth until it reaches a plateau for 0 at certain distance, and the distance is normalized by the size of the hurricane. In this case, the size of the hurricane is characterized by the radius of the outermost closed isobar here. And there are the different metrics or different features of this functional form are parameterized by the category of the hurricane, like the slope of this initial decay, this initial part of the decay, and also some metrics that interact with the distance from the site to the eye of the hurricane. So we fitted this assessment, we fitted this functional form and had this part ready for module 2 to be coupled into all the other pieces of our analysis. So then we reviewed the literature on solar irradiance failure and functionality after hurricane. There is much less information about this part of the analysis as there is for the other parts of the analysis, the other two parts of the analysis. We found a couple of PhD theses on that. This is the thesis from Dr. Goodman at Georgia Tech, where he developed an analytic formulation or an analytic model of a fragility function of solar panel failure associated to a structural failure mechanism of gelding in the rails and in the cliffs of the solar panel and the wind conditions at the site. And here you can see that out of his model, we can see that the solar panels are generally, I would say, strong in his model. Let's say that to have a significant likelihood of failing, you have to have a category 2 wind or higher here. However, what we see in data, it's a little, I wouldn't say a little bit different, but we find failures in the solar panel. This is a picture from the Rocky Mountain Institute here that they kindly share with us here. And you can see that the solar panels do fail. And actually we got an assembly of 22 data points to analyze the solar panel failures. So I might be redoing this part of the analysis in the next few months with this new data here. But we use this in our assessment so far. So this is the third piece of the analysis. And then we put all of it together here to focus on the fourth part of the analysis, where we actually predicted what's the generation during hurricane. And as I mentioned before, first we assessed the full suite of the full catalog of hurricanes here. We coupled that with the irradiance decay during hurricane conditions, and we coupled that further with the vulnerability of solar panels here. And then here in the plot at the center here, I'm showing you generation in the solar panels, instantaneous generation in the solar panels in Miami. The gray lines here are showing you most of the hurricanes in the catalogs, and it's wavy because the radiance goes up and down during the day, goes up during the day and down during the night. And then I'm showing you, I'm highlighting in the other colors here from green to purple, some of the extreme events that happen and how the solar panels respond. So the plot or the line, the curve in green here is showing you an event that it's not as extreme, it just occurs every 3 years. And you can see some reduction in the ability of the solar panel to generate energy. And this is mostly due to the cloud conditions. But then you can go to events that are more extreme and occur less frequently, like the one in 1,000 years. And you can see that your ability to generate is zero, basically because this one most likely triggered a failure in the solar panel so that it cannot collect any energy. And then you see in the plot at the right here, the cumulative version of the plot in the center. And it's showing how, and for different hurricanes, most of the generation remains unchanged. But then you have some of the extreme events that usually happens in risk analysis, where that triggers most of the undesired outcomes, up to points where for the event with recurrence of 333 years and 1,000 years, you have zero ability to generate solar energy. So this is a plot for Miami, but we repeated the analysis for other three counties besides Miami. We got Galveston, Texas, Miami, New Hanover in North Carolina, and also New York in New York. And here you can see that the lower the lines are, the lower the y-axis reaches at the time of 4 days after landfall, the worse your ability to generate this. And you can see that Miami behaves worse than a solar panel in Miami would behave worse than in the other states, and that's associated to the higher winds that they have, and also the higher likelihood that they have to experience higher categories, which also increases the likelihood of a solar panel failing, and also decreases or intensifies the irradiance decay during cloud conditions. You can see that Galveston and New Hanover do perform similarly, and New York tends to perform a little bit better because it's in the northern part of the US. So you can start seeing these non-uniform effects, spatial effects of the generation of energy out of this analysis. So now we're going to focus on what happens after day 4, or during day 4 and the cumulative generation. We're going to see the same plot, but for all the counties in these maps here. So here I'm showing you cumulative generation for a hurricane with a 10-year return period. And this is over the entire East Coast of the United States here. And if you compare this to the normal conditions, you won't see much of a difference for the 10-year return period. Most of the decrease in the ability to generate energy comes from the hurricane decay due to the cloud conditions. But then you can start moving to the more extreme events, the ones that occur every 100 years or every 1,000 years. And in 100 years, you start seeing some decays that are significant, especially in Miami, on some of the southern parts of the US. And then you move to the extreme event that occurs every 1,000 years here, and you can see that the decays in generation are much more significant here. And this is mostly triggered now by the failure of the solar panels. So you can see that now. So this concludes the second part of my presentation, where we, again, we focus on a large geographical extent. And we saw how we can couple hurricane models with solar irradiance model and solar vulnerability models to see what's the generation after or during hurricanes. So now I'll just summarize the results and my work with the conclusions here. So first, I like to highlight again that the traditional power system is extremely vulnerable to natural disasters. We can see that with plenty of examples from earthquakes and from hurricanes. And however, these distributed energy resources that we introduce into the system might change this situation as they are introducing generation in closer proximity to the end users. And here we're developing methods to see and quantify what's their effect. First, I show you a model to account for how the solar panels and microgrids bring energy after earthquakes in a city, and we saw this microgrid behavior. And one conclusion out of this analysis is that in San Carlos City, we saw that the current adoption of 8.5% is still insufficient to sustain loads when there is an outage. 8.5% is still very low. However, if we, under certain adoption rules, we can see that with 20% adoption or more, we can start seeing yes, I guess I lost you for a bit, but yes, now I'm back. Okay, so we saw that if we let the market do its work, then what's going to happen is that you introduce heavy disparities in the community. And that was triggered by the overall rule where just the people with the largest saves adopted first. And then finally, we saw how a hurricane application in these codes of the United States shows that the risk is non-uniform in the US, the risk of not having enough generation out of solar panels. And that might introduce, or that might request that we design different policies according to where you are in the United States. Our next step out of this hurricane analysis is to focus on a city now and see, like we did in San Carlos City in California, and see what's actually the gain from adopting a microgrid there. So with that, I like to conclude my presentation just by highlighting here my collaborators and my funding sources, and just reminding you that while we saw that our power systems are vulnerable to both hurricanes and earthquakes, it also happens with wildfires, as we saw in last year in California. So with that, I thank you for your attention.
Great, thanks, Louis. We can start our Q&A session. So the audience, please put your questions in the Q&A chat room, and we will go through the questions. Maybe first to clarify, two clarifying question, Louis, if you go back to slide 22, please. 22. Would that be a typo here? I think this is probably Hurricane Katrina in 2005.
You're right. Yes, it's a typo. Yes, you're right.
Okay.
Thank you for catching that up.
Just clarifying. And then go to 25, slide 25. So here, you mentioned that the vulnerability curve seems showing that you only get damage when you get category above category 2, and you mentioned there's a lot of damage observed after Hurricane Maria. So Hurricane Maria was category 5 for some duration of time, yes. But the wind will vary from place to place. So I'm wondering, for this kind of, do people have collected data of damage of the panels and also the wind information at the site to evaluate such a vulnerability curve? Do you know?
Currently, there are not many studies, quantitative studies on that. There are many descriptive studies of what they saw on the field. Actually, I was in contact with researchers from the Rocky Mountain Institute, and they collected the failures of, well, they surveyed 22 or close to 25 projects with solar panels, and they have data on that. So I think we have enough material now to analyze that. But before that, there are no studies that are data-driven assessing these vulnerability functions. All of these ones are more analytical, barring wind conditions and doing numerical analysis to see how some structural failure mechanisms might develop on the solar panels.
Yeah, be interesting to follow if the new data becomes available.
Mm-hmm.
Okay, so we have questions from the audience. First, from Professor Ecker Weber. For the frequency of extreme hurricane event plots, for example, solar generation for time after hurricane landfall, are those categories, for example, 10-year event, based on traditional historical frequency estimates, or do they incorporate the climate change related trends that makes real extreme events less real?
Mm-hmm. No, these are only hurricanes under current conditions. So this doesn't incorporate climate change. Climate change might exacerbate, will exacerbate probably these curves, make them lower. As a result of categories, I didn't show that here, but I revised that. It depends where the hurricane passes by an area close to the county or not. Yeah, I guess I'm not showing that here, but you can see similar trends here, where higher hurricane categories just decrease your ability to generate energy.
Just to add a note here, so here for the first step of analysis, we are focusing on the so-called historical climate condition or current climate condition. So all the storms are generated for this condition. But the methodology can be used to generate storms under future climate change scenarios. So actually, I think the next step of the research would be incorporating the effects of climate change and see how that would affect results. Great, thanks. So next question from Jane Fox. Are you working with the Puerto Rican government and or PREPA?
No, I wish. I've been reviewing plenty of data and reports from there, because the stories are incredible there, where people lost power for several months and they had to rely on diesel and power generation. I haven't been able to get enough data to start some analysis there, but like any connection or data you might know of, it's highly welcome. Yeah, it's very incredible what happened there.
Mm-hmm. Okay. Next question from Anne. Can you explain more about market adoption versus uniform adoption of microgrid platforms with regard to both the model assumptions and the real world implications?
Yes. So here, I guess there are two things here. First, we assume who adopts first, right? And there are some models that track how people might adopt in the future at very local scale. But here, we just wanted to test two very different philosophies of adopting that are very distinct one to another. The first one is just an adoption that's based on pure market rules, whether the ones who save the most are the ones who are going to adopt the first. And in the other one, we introduce a slight variation to that, making sure that each microgrid had the largest adopters, the largest consumers to adopt, but in a way that each microgrid has the same number of people who adopt, the same number of households who adopt. Whether the current market trends are similar to any of those, I don't think they are to any of these ones too, because these are abstract models, but they are kind of in between. They're in a situation in between, and it's going to depend on a stimulus from regulators, from policymakers, to make them look more like the ones, an adoption that looks more to like the overall adoption or to the even adoption. Because for the even adoption, you need to have potential incentive, because people who don't have probably as much, they are not the big consumers, they are not the ones who are going to save the most. These ones are probably going to need some kind of incentive to adopt. So that's my answer on that.
Okay. Next question is from Ninand. Ninand says, thanks for the presentation. I'm curious what causes a large improvement in performance when adoption rate goes from 10% to 15%. I think this was on slide 18 or so.
From 10?
What causes a large improvement in performance when adoption rate goes from 10% to 15%.
Okay.
It's about slide 18 or so.
So I think 18 is, it must be slide this one. Yeah, well, here, you're right. If you focus on the median, it looks like the one below has a very dramatic change. I think it must be because okay. I think what's happening here. I think what's happening here is that when you take adoption from 10% to 15%, you're actually increasing a 50%. You're introducing a 50% capacity on the system, which is significant. It doesn't seem, in absolute terms, doesn't seem as much, but in relative terms, it seems like a significant change. So that's what it's triggering, this change. But I'm gonna double check that, Ninat, and I'll get in touch with you to have more clarity on that answer.
Okay, next question from Kai. What would be the minimum adoption requirement rate to ensure basic power supply to residents for survival, for example, heating for winter?
I don't know if I understand that question.
So what would be the minimum? So you show the adoption rate, that's based on probably, maybe it's ideal rate. So the question is, what would be the minimum rate that can use for surviving?
We did some numerical studies on that, and it depends. It's very related to how much you have adopted in the first place. Under a net zero scenario, it depends on what season of the year you are, and it depends on on this factor here, on how much demand you have, reduced demand you have after the earthquake here in this case. So it varies according to that. Ideally, if you are going to share energy, and if you're going to reduce your demands by 50%, if 50% of the houses have it, then you're going to be okay. That's more or less kind of what the intuition behind it is. Now, what happens in reality is that these reductions in demand are very non-uniform, and it depends. I mean, for residential, it might be more uniform, but you also have industries, you have emergency responders, you have stores, and they might actually increase their demands for power systems. So it's not a simple answer for that. It's very stakeholder specific. But again, it's linked to what's the level of demand that you need for a specific stakeholder.
Okay, here's a question from Richard Moss. Thanks for a really interesting presentation. What are the factors that you considered in estimating the number of days it takes to get solar generation back online after a storm?
That's a very interesting question. So now we assume that the solar panels are going to be, well, the ones that do not have earthquake damage or do not have hurricane damage are going to be working continuously. Now, that might not be true if your solar panel still has the inverter in the grid, right? Because a lot of solar panels that are installed now still need the grid, which might be unintuitive, but they do need the grid because their inverter is there. Now with the introduction of batteries, that might change because your solar panel is going to generate and it's not going to need the grid as it does now, and you can just store energy by your own. So that situation might change. I guess in short, my answer is that we consider them that they're going to work as if they have a battery, so they're going to be continuously working. So that's what we did now. And hopefully that's where the grid will, that's how things will be in the grid, because that feature will make the grid more resilient.
Okay, so let me ask you a couple other questions. So previously, Eka asked about the effect of climate change on storms. So if you have climate change making the storm stronger, so the damage is increased, and the solar generation may be further reduced.
course.
But on the other hand, if climate change may also increase solar generation. Is that possible? And so I'm trying to think about which way the climate change is actually affecting the production.
That's a very interesting question. I haven't looked at that, but I understand that, intuitively, if you have a warmer climate, that might have a positive relationship with the intensity of the global horizontal irradiance, for example, right? Under that condition, we have an increase in solar generation. But I haven't looked at that. I think it's it's a fascinating question. So I think, we should look at that.
Mm-hmm. I have one more question. So you talked about hurricanes and earthquakes as two hazards and disasters. Is there opportunity or need to think about them together? I guess there are areas that can be affected by both. So if you design the system considering both, would that be more effective?
I think, well, I don't know on the top of my head if there are places that, well, I guess Mexico is exposed to both earthquakes and hurricanes. There are some places that have that. Japan is also exposed to both. So yeah, we should think about those because they can happen, but also there are other things that can happen simultaneously. Like for example, now with COVID, which is stressing heavily the demands on the system because people are working from home now. That's changing the profile, the energy demand, and stressing the power system. That coupled with the hurricane season, we don't know what's going to happen there, or with heat waves, we don't know what's going to happen there. So there is, I think, an increasing need for us to look at concurrent disasters and seeing what's the effect of that on the resiliency of our grids and how the grids are, what's the grid ability to give power to emergency responders, stores. We've seen some of that also in Croatia. We had an earthquake a month ago during the COVID outbreak, and in Mexico also we had an earthquake a few weeks ago. So these events happen, and as we have more disasters that last more than days, like weeks or months, like COVID, then it's much more likely that we're going to see these events happening together. So yeah, I think there is a need for studying simultaneous events.
Okay, yeah, I think we don't have more questions. Well, time is up. So thank you very much, Luis.
Thank you.
Now I'm handing it to Charlie.
Yes. So Luis, thank you again for that excellent presentation. I also want to wish you the best of luck this coming year when you join the faculty at NYU as an assistant professor of civil and urban engineering with a joint appointment at the Center for Urban Science and Progress, correct?
Thank you. Yes, that's correct. I'm excited.
Excellent. Well, thanks again. I also want to acknowledge the Endlinger Center staff who are working hard behind the scenes to support the creation and delivery of this webinar series. And again, I want to thank you all for attending today. Next week's webinar will be at 2 p.m. on Wednesday, July 15th. And we're pleased to be co-sponsoring the event with Dartmouth College's Arthur L. Irving Institute for Energy and Society as part of their new energy speaker series, Conversations with Early Career Energy Researchers. Dr. Rebecca Ches, a former Endlinger Center Distinguished Postdoctoral Fellow, who will also be a new faculty member next year at Purdue University, will discuss how setting goals for climate can inform energy storage designs. You can find a link to the webpage listing the full speaker series and the registration sites posted in the chat box. We look forward to seeing you at future talks. In the meantime, stay safe and healthy and have a good week.